Yeah, so I'm Trevor McCrary. I'm a grad student at the Georgia Institute of Technology, and I'll be presenting on integrating Chapel programs in MPI-based libraries for high-performance graph analysis. This is a project based on a summer project I did with Sandia National Labs as a summer intern last year, with significant help from Karen Devine and Andrew Young. So the goal of this project was to allow users to use the right tool for every job. And so throughout this project, we had the general program flow where Chapel will read in data and then share it with a MPI based library, which can then do some more analysis on that. And we used the Grafiki library, which does high performance graph analysis. So Chapel's parallel global address space enables analysts to easily manipulate parallel graph data. And for our purposes, we use Chapel to extract the largest connected component from a graph via label propagation. And then Grafiki's linear algebra based parallel graph algorithms enable efficient parallel graph analysis. And we use the vertex hitting times algorithms. In composing these tools was challenging. We have the different parallel paradigms of the parallel global address space in Chapel versus MPI and Grafiki. We also have different data formats being used, with edgeless being a method of storing a graph in Chapel, whereas Grafiki uses a matrix. Huge graphs are also prohibit copying or reformatting the data in memory. So this project provides three new approaches to integrate Chapel graph manipulation with Grafiki graph analysis without requiring additional copy of the graph to be stored. The first method is the simplest, with a direct call from Chapel to Grafiki using Chapel's C interoperability interface. The second one has a separate Chapel and Grafiki process running concurrently, which access a shared mmap memory region. And the third is similar to the second. We have Chapel interacting with a containerized Grafiki process that access the mmap memory. And I want to cover why we have the requirement to not copy data, and it's because it allows us to solve larger problems. There are two approaches that someone could take when sharing data between applications that fall short. The first one being is that sharing data with files is simply not scalable. So we have the situation where Chapel reads in a graph data, modifies it, then writes the results out to a new file. Then the C++ program reads the new file and performs some analysis with it. In this case, the file IO is terribly slow, and doing this method this way, we have a copy of the data stored on both programs simultaneously, which can cause issues if they're running concurrently. Another option would be sharing data with native data structures requires copies to use extra memory. So in this case, Chapel reads in the data, modifies it, and shares it with our C++ program, which then needs to rearrange this data in some way, which would create a copy of the data on the C++ program before it performs the analysis with it. And to solve this issue, the C++ program needs to have general abstractions to use data in any format. Our Grafiki library relies on open source Trilinos for linear algebra classes and linear and eigensolvers. And we replaced Grafiki's use of the concrete CRS matrix class with an abstract row matrix. And in the row matrix, the user provides an implementation of key operations such as sparse, matrix vector multiplication, and norms. So our new Chapel-based row matrix uses an edge list directly from Chapel to perform its matrix operations, which requires no additional copy of the data. So there's a depiction of the first approach we have, where Chapel calls Grafiki through Chapel's C interface. We have an edge list depicted using a block domain distribution, where each color represents a locale's own memory. And then each Chapel locale directly calls a C function in a co-for-all loop with a pointer to its local data. And then our external C function instantiates a row matrix from the edge list pointers and calls Grafiki, which then performs its analysis using the row matrix. The upside of this is a simple proof of concept for data sharing between Chapel and an external library. The downside is that it's very intrusive to the user, because the user needs to link Trilinos in Grafiki with their Chapel project. To go into the details of this first approach, we have to coordinate Chapel locales and MPI ranks. So for our case, we have an equal number of Chapel locales and MPI ranks, and then calls from the Chapel two Grafiki must be made from each locale in parallel so that all locales can enter Grafiki together and avoid hanging on an MPI collective call. In Chapel's Coverall launches one task per locale. We have a short pseudocode snippet at the bottom here showing locales providing pointers to the local array when calling into our C function, which will interact with the Grafiki library. For the second approach, we have two concurrent processes which share data in mmapped memory. For this, Chapel creates edgeless in what we've called the shareBlockDomain that uses mmap memory. I'll go into more detail on the next slide, but this is a modified block distribution domain module that creates an mmapped memory region pointer instead of allocating memory in its usual fashion. And then the Chapel program signals to the XML process that's ready to begin by using a POSIX semaphore. Our C process then instantiates a row matrix in the same manner using the edgeless pointers in mmap memory. And our C process calls Grafiki, which then does its analysis as normal. This is less intrusive to the user because they can use Chapel as normal and only have to substitute the share block domain for the block domain in their code for the shared data. So for the details on this, Chapel domains in general describe a distribution of data across locales and manage global address space indexing. And the Chapel's block domain assigns a contiguous chunk of global arrays to locales. Each locale has a separate allocation. Our new share block domain replaces the local array allocation with mmapped regions in shared memory. And separate mmap backing files is provided for each shared array. And this is necessary for if we have multiple locales on one node. If the backing file is the same, they will essentially point to the same section of memory and will have a duplicated chunk throughout the distributed array. Backing file names are then shared between processes through a small metadata file to communicate to the MPI-based process what the backing file names are. And again, Chapel users simply substitute the share block module for the block module in their code. And for our third approach, we have Chapel interacting with the containerized Grafiki to further simplify user experience. In the same manner as before, Chapel creates an edge list using the new share block domain, using the mmap memory. And then the Chapel program signals to the external C process to begin by using a pseudo semaphore, which is essentially just a single mmapped integer. We ran into issues with the container where the namespace of semaphores were unable to be accessed by the container. But the container can access the mmap memory without any issues. So we have a single mmap integer that's essentially a flag to be 1 or 0 to indicate which process's turn it is to execute. This is the least intrusive method because the container handles the details of building and running the C process in Grafiki. And so we perform some demonstrations with these approaches on a Chapel, MPI, and SMP based systems. Our shared memory Chapel was on a Xenon machine called Kahuna. This used a single node with multiple locales and multiple ranks per node. This is also the machine where we used our containerized Grafiki approach with Singularity. Our MPI enabled Chapel was on a Cray/Haswell machine called Neutrino. This has a single locale and single rank per node using multiple nodes. And so we compare using approach 1 with the Chapel interoperability and approach 2 being the separate processes to look at the Chapel label propagation algorithm and Grafiki heating times algorithms runtimes between the two methods. So here's our runtime graph. We did a small scale test and a large scale test using graphs from Sparse Suite, which is an open source collection of sparse graphs. This graph was BCS STK29, and it had 600,000 non-zeros and 14,000 rows and columns. It's important to note that we have NA written in several columns for the Kahuna machine. That's because it was using Chapel SMP 1.23, and we're unable to run approach 1 on more than one locale. And the big takeaway from this was that the mmap memory appeared to run equal performance using Chapel's usual memory. Between 1 and 2, we saw no decline in performance across the board for the small scale test. Our large scale test used a graph called gap_cron with 4 billion non-zeros and 134 million rows and columns. We have the same issue as before where our Kahuna machine has NA in columns for more than one locale due to Chapel SMP 1.23. We did have a noticeable loss of performance on the neutrino machine for the Chapel label propagation algorithm. We're not certain on why this occurs, but our hypothesis is that we were using Chapel 1.23's block domain as a template for shareBlock, while Neutrino used a version of Chapel 1.24 for its regular block domain. On the MPI-based library side, though, we saw no performance penalty for using the mmap region as opposed to Chapel's typical memory allocation. So to recap, this project presents 3 new approaches for sharing data between Chapel and a C++ MPI library without making copies of the data. And the major factor behind this is to allow Chapel users to leverage existing fast MPI-based libraries without having to fully re-implement them in Chapel. For future work, we'd like to see extended operability to different Chapel distributions. We currently only have this working in a block domain because it's very simple with the contiguous memory and sequential indexing. It would be easier to implement different distributions if there was an option in Chapel to accept a user-defined allocator in these distributions. And lastly, some points that were out of scope for our project was to analyze container performance. We simply didn't have time during this project to go into that, but we assumed that there wouldn't be a significant penalty using the container versus not. We also didn't have time to analyze the Chapel and MPI library integrated performance against a pure Chapel implementation. That was mostly out of the scope for the project, and again, to allow Chapel users to utilize existing MPI-based libraries rather than fully re-implement them in Chapel. All right, so that's all I have for my presentation. Thank you for listening. We can go into questions if there are any.
Thanks, Trevor. So again, if anybody has a question, you can raise your hand and then ask your questions, or you can write it in the chat and I'll. Okay, so we have 2 questions. So Michael Ferguson was the first. Michael, if you want to ask your question.
Hi, yeah, thanks for the talk. This is interesting work. One of the things I'm curious about is it looks like you've got this way of sharing the edge list between the 2 implementations using mmap. But having like an array with an edge list in it is one of many ways of representing a graph. And there's also sort of sparse techniques and maybe higher level views where you like have some kind of graph object and you interact with that. I was curious if you had any thought about the sort of other, like it sounds like this is sort of offering a low level view of a graph as an array. And is that correct? And if so, have you thought about any higher level sort of programming APIs for working with the graph? Thanks.
I don't remember it specifically. So I was reading in these files as a matrix market format, which gave out an edge list. And I assumed that that was just at the time the easiest process was just to read in that data and rather than modify it, just go ahead and use it as is. If Karen Devine's on the call, she might have a better background on that area, but I don't think I looked into any specific other methods.
Sure. So thanks, Trevor. Great job. So Trevor was tasked with doing a proof of concept. And what we learned was that certainly this approach could work, and we could extend it to other data structures that are in Chapel and other representations of graphs, as you mentioned. That would the key step was replacing the allocator in the block distribution to point to mmap instead of to the malloc call that one would normally use in C. And so we could go through and retrofit other data structures to do the same thing. But that was part of our motivation for this suggesting that Chapel just accept an allocator would be for it to substitute a user-defined allocator that would use mmap to be used in any of the data structures. And that way we wouldn't have to retrofit them all. Rather, this allocation could be used in all of them. And I really liked the synergy between this talk and the previous talk, because I could imagine that being used using the fabric memory as well.
Thanks.
Okay, we have another question from Ben McDonald. If you want to talk.
Yeah. Hi. Yeah, I was just curious. So you mentioned the three different approaches that you implemented this in, and I was just curious, kind of at an anecdotal level, like which was the most difficult and which was the easiest for you to implement in Chapel of the three approaches?
The easiest was probably method one. I think I got that working early on in the project, just because like there was already a lot of documentation existing for the C interoperability, being able to call C directly. There wasn't much of a difficulty going between containerized and the approach 2 and approach 3 for me. A lot of that work was covered by Andrew Young of just getting the container set up and making sure that all of the requirements were there. Approach 2 was definitely just the hardest overall. I did a lot. I talked with the Chapel team last summer on the discourse group kind of forum to figure out where to find all of the allocators and what I should be modifying so that there isn't a copy happening in the background behind it.
Okay. Yeah. Thank you.
Thanks for the question. So there is another question from David Wonacott who wants to ask it. So can you unmute and ask your question?
Similar question, but from the point of view of the user, not the question of how hard was it for you to implement this, but there are the three of them. And my understanding was the goal was the third one would be easy for the user, and containerizing would get rid of some of that burden of the second one. Is there how would you, if you imagine containerizing the first one so that there's C under the hood, but it's not shared with mmap, is that possible or is that not possible? And would you expect it to be harder or easier than containerizing the third one in terms of the experience of the user?
So containerize the first one where we're using like the external C.
Yeah,
Okay.
but containerize that so that you just call what looks like a Chapel function and then it calls the external C.
I haven't thought about that. I don't know if that's doable. I think interesting that would be a simple option to not worry about a lot of the backend issues.
Yeah,
there is some
one set of backend issues that you know into another set of backend issues that you don't yet. So we can hope it would be better. Just wondering if you'd given it thought and rejected it for some reason, or if you just hadn't explored it in the limited time you had.
I think from my perspective, this was approach 1 was like the easiest to implement, but the stretch goal from my manager was always to have the 2 separate processes. So I didn't really consider beyond
that was a
this
design
going
goal then. Okay, that makes sense then. Yeah.
Yeah, I don't know if anyone here has ever compiled Trilinos and Grafiki, but any time that we can spare a user from having to do that is a good time.
Okay, that makes sense. So that in particular would not be containerizable because you'd have to do that compile.
For the first approach.
Right, for the first approach, even if you tried to containerize some things, you couldn't containerize the compile process.
Yeah.
Yeah, it makes sense. Thanks.
Yeah. We have another question and a comment on the chat. Now it's 1:45. Well, that's my time, but so I think we need to start the break. But maybe I can relay that question since anyway it's a break. So the question was from Akiro Ayashi. He says, I know you're going to analyze the container performance later, but you expect the container version adds some overhead.
We asked Andrew Young specifically about this, and he said in his experience with other projects, they haven't seen significant overhead from doing the containers, but we have not analyzed it in this context yet.
Okay, thanks.